maybe not understanding things as well as they should be. You got to worry about that too. Like everything we do in lab is designed that way for a reason, right? Make sure you understand all those derivations, all those, why things worked out, why the circuits were connected the way they were, why the voltages were the way they were. If they didn't come out the way you anticipated, why not? I mean, you can't just, you got to really attack this stuff. So anyway, I will not be here on Friday, but you are having a lecture. Elliot is going to be giving the lecture. And at the end of the lecture, Elliot will probably give you a quiz. All right? That quiz will probably look a lot like something from Exam 1. That, to me, should be like freebie. Okay? That's like free points for everybody. So it should be, right? I mean, if you have the solution, and I'm telling you the exam is coming, that's my motivation to make sure that everybody opens the solutions and studies them. So please, between now and Friday, open the solutions, study them. Right? At the end of the semester, someone's going to say, can you drop a quiz grade? I'm going to say, but I gave you a quiz for free. Right? Everybody should pick up a 5 on this, or a 10, or whatever he's grading him out of. Okay? So there you go. Thoughts? Questions? Concerns? All right. I want everyone to kick ass in this class. Like, seriously, I'm enjoying teaching this. I want you to do well, but, you've got to bring your A game. This stuff's not easy, and it's not immediately obvious. You've really got to, here we go, I found the right spreadsheet. You've really got to come prepared to put a lot of time into this. Okay. We're going to continue our analysis of circuits, and I understand that Elliot has been teaching you some tools for doing, some MATLAB tools for analyzing these circuits. Is that correct? Good. So I've been sticking with Excel tools, which is, it's a little bit old school in the sense that no engineer really uses Excel, but I do like it because it lets you see all the numbers and touch all the numbers in a way that's a little bit easier, I think, just for a first pass. So I think I'm going to kind of stick with that for the time being, in the sense that I want you, for lecture, I think the Excel tools maybe make a little bit more sense, just because it lets you visualize all the numbers and play with the graphs. But you definitely need to be learning the tools that Elliot's showing you in lab as well. I would say that for every circuit that we look at, you should be able to build yourself a little Excel spreadsheet that models it, but you should also be able to get that same answer in MATLAB. So for example, those transfer functions, right? Those low-pass filter roll-offs that we were looking at in class on Friday, you should be able to use the TF command and the Bodhi command or whatever Elliot's been showing you in lab and generate the same plots, right? There's only one right answer. You should be able to get it using whatever tool that you have. So I would encourage you to familiar yourself with those tools and make sure that they are in agreement with each other. And if they're not in agreement with each other, that's actually a good thing because that offers you an opportunity to figure out where the disconnect is, right? And you always learn something there, right? Maybe there was a number that was supposed to be somewhere different, or I don't know what, but it helps to figure that out. Okay, we good? My goal today is to get through 1, maybe 2 more circuits that we're going to analyze using our same phasor function analysis. So let's start with this one. So same thing. It's almost identical to the circuit we looked at before, except all I've done is I've reversed the locations of the resistor and the capacitor. All right? And I'm going to assume that my input is a cosine with some frequency omega. And I'm going to leave omega as a variable because I wish to vary that frequency. All right? I might try low frequencies, might try high frequencies. And I want to know what kind of circuit have I built for myself. Have I built a high-pass filter, a low-pass filter, or whatever pass filter? All right, so generally speaking, what will be my output voltage? What can I say without doing any more analysis? Cosine. Any cosine? Same frequency. honestly, if you get nothing else out of this entire freaking semester, okay, I would just care that you learn that when you stimulate a circuit with a cosine, what you get out is a cosine at the same frequency, okay? Because that sort of underpins like 4 classes, okay? It all sort of works on this concept that cosine in equals cosine out. All right, when you get to my signals class, which I'm guessing I'll see many of you next semester for signals, it's the same nonsense, okay? You know, we basically build an entire semester of signals around the concept that you can take any old arbitrary signal, break it into a sum of cosines, and then think about how each one of those cosines is treated by your circuit. Then you take all your cosines as they come out of the circuit, rebuild them back into a signal, and that's your answer. Okay, when you go to controls, everything's a cosine. Right? When you go to communications, I mean, it's all this. This is the nugget. Right? This is what it's all about. All right. So if cosine stays the same and omega stays the same, what potentially could be different? Magnitude and phase. So all this game we're about to play is about figuring out the magnitude and the phase. Okay? And our tool for studying that is, we said, the phasor approach. And we said that the capacitance, the impedance of the capacitor, could either be thought of as 1 over j omega c, or we could think of it as 1 over omega c, phase angle, what was it, minus 90, minus pi over 2. Okay, so those are entirely equivalent, right? Both of these are complex number. This is basically the rectangular form, and this is basically the polar form of the same number. All right, so how should we treat this circuit? How should we figure out what V out equals? What was the trick we used last time? Voltage divider. Couldn't agree more. Right? It is a voltage divider, right? Yes, sir.
Would it be too much to ask to make your thetas with a straight line? I'm not sure what number here is.
This is a phi, not a theta, but if you want it to be a theta, we can do that. Like that?
Yeah, I was wondering here.
All right, we'll do thetas. It's all good. We can be accommodating. All right, so how do we work this before? We said voltage divider, right? I mean, it is a voltage divider if you think about things as impedances instead of resistors. So how's that voltage divider equation going to read? V in times R over, right, R plus 1 over j omega c. Ugh. Okay. Nobody panic. All right, so let's see if we can clean this up a bit, because it's a fraction with a fraction in it, okay, which is pretty bush league. We don't leave things like that unless we really have to. So what's my easiest way to clean this thing up? Yeah, so the standard trick is to multiply this by 1. Okay? Can I do that? Totally. You can always multiply something by 1. We know that doesn't change the value. And if I'm slick about my choice of 1, in this case, j omega c over j omega c, what that'll leave me with is V in times j omega RC over j omega RC plus 1. Okay, so remember, this is a complex expression. Let me just write this out in words. This is a complex expression that tells me both the magnitude k and the phase theta for my output. That's why we do this. That's why we do the phasor analysis. It's because with one equation, right, we did one equation, one voltage divider equation, we simultaneously, in this term here, we're simultaneously being told the magnitude and the phase. Right? There are other ways of doing this, but they would require a separate calculation for magnitude and a separate calculation for phase. So I'm giving you 2 for the price of 1. The reason you get 2 for the price of 1 is you're using complex numbers. And complex numbers are, in fact, it's one complex number, but it has 2 pieces, right? A real part and an imaginary part. So it's like this mathematical sleight of hand that we're playing. We're handling one complex number, but it's got 2 bits in it, right? One bit is telling you about the magnitude, and one bit is telling you about the phase. So it's cool, right? One equation, 2 answers. It's not often you get 2 things for the price of 1. So let's go ahead and calculate the magnitude and the phase of this expression. So let's start with our numerator, j omega RC. Can we express that in terms of magnitude and phase, please? What is the magnitude of j omega RC? Absolutely. Omega RC. How can I get that? That's just by inspection? That's pretty awesome. 2 ways, right? It's really real part plus omega RC, j omega RC. And if you apply the formula, it's the square root of the real part squared plus the imaginary part squared. So it's the square root of 0 plus omega RC squared, which is just omega RC. Okay, that's easy. Angle. Now what's the phase angle of my numerator? It's always inverse tangent of imaginary part over real part. So it's inverse tangent of omega RC over 0. There's no 1. There's no 1. It's inverse tangent of omega RC over 0. So what's inverse tangent of something over 0? Inverse tangent of infinity. Pi over 2. And this should surprise nobody. Look at this. You remember your complex number axis? Real and imaginary? Where is my numerator? Where is j omega RC on this graph? Look, what's the real part of this complex number? 0. The real part. 0, right? The real part isn't positive and it isn't negative. The real part's 0. The magnitude, and then the imaginary part is omega RC. So, what's its magnitude? What's the length of that stick? Omega RC. What's the phase angle? Good. Okay, let's do our denominator. Our denominator is 1 plus j omega RC. So, what is the magnitude of my denominator? Yeah, now we got the whole the real part squared, well, 1 squared plus omega RC squared. Phase angle, arctan, imaginary part over real part. Now, my imaginary part is still omega RC, same as before, but instead of dividing by 0 and taking the arctan of that, I'm dividing by 1. So it's that arctan. Okay, and again, this shouldn't be surprising. This shouldn't be surprising because now my complex number has a real part of 1, an imaginary part of omega RC. So here's my complex number. All right? What's the magnitude of that complex number? If we look at it geometrically, what's the magnitude of that line? Pythagorean theorem, y'all. Square root of 1 squared plus omega RC squared. Right? That's Pythagorean theorem. What's that phase angle equal? Inverse tangent of opposite, which is omega RC, over adjacent, which is 1. Okay, so let's combine these to get our final answer in phasor notation. So I'm going to go ahead and do the division now. So when I've got a complex number in the numerator and a complex number in the denominator, how do I get my final answer? How do I combine that? What do I do with the magnitudes? Divide the magnitudes. So it's omega RC over root 1 plus omega RC squared. Okay, so that's my magnitude. Angle. Now I'm going to subtract the phases. Pi over 2 minus inverse tangent of omega RC. Wow! That is some high octane nonsense. Okay? But it's right. Like we've done the analysis correctly. So the thing is that realistically, from an engineering perspective, okay, the part that you would really need to be good at doing by hand, like when you go get a job, no one's going to pay you to do this. Okay, we have computers that do that. All right. Realistically, you need to be able to get it this far. Okay. Once you can express the complex transfer function, you can shove it into MATLAB or whatever tool you're using, and it'll crunch those numbers for you. That's not hard. But because you're in circuits too, and you got to learn this stuff at least once, right? My obligation for you is to show you what this actually means, right? That what actually happens when you look under the hood, break it into pieces, and say, oh, okay, that's what that does. I understand. I don't ever need to do it again, but I understand. That's kind of where we're at. So I need you to know this. I'm going to test you on it, okay? But I'm also going to make sure that you understand that, and you know how to use the tools that basically say that the party kind of stops here. Okay, this is where you need to understand. Okay, so this is so we started by saying my output would have a magnitude and a phase, and look what we've done now. This is your magnitude, and this is that's your phase. So let's see, what is let's look at our magnitude. What happens at the very lowest frequencies when omega is really, really small? What is my magnitude K? What happens to my magnitude K? If omega is small. Start in your denominator. What happens to my denominator when omega is small? Which term dominates? The 1 or the omega RC squared? If omega is small. 1, right? If omega is real small, like 0.000001, that's pretty small, right? Then you can say, well, forget compared to 1, that term is pretty minimal. So we'll ignore that. So now you've got radical 1, which is 1. So that goes away. You're just left with omega RC, and we just said omega RC was really small, right? So as omega is really small, this whole expression becomes really small. Okay, so if we were to make a plot, and right now we're going to make the plot using the hand waving method, and then momentarily we'll make the plot using the Excel method. So if we were to make this using the hand waving method, where we put frequency on the x-axis and amplitude on the y-axis, we've just said that at low frequencies, my output is going to be a cosine that's really, really small. What happens at high frequencies when omega is really big? Start in the denominator. That's the only thing, that's where it all starts. If omega is really big, who wins in the denominator? The 1 or the omega RC squared? There we go. Good. So now my denominator can be, we say forget the 1 because it's insignificant. So I've got the square root of omega RC. So the square root and the square cancel. You're left with omega RC over omega RC. 1, right? Even I can do that math. So at high frequencies, At high frequencies, your amplitude is 1. Meaning that if whatever your input is, so let's say at high frequencies, your cosine that comes out will have the same amplitude 1 times the cosine of the amplitude of your input. Okay? So here, this is like, so this 1 means that V out equals 1 cosine omega t plus whatever the phase is. Whereas over here, it's like saying V out equals 0 cosine omega t plus whatever your phase angle is. 0 or very small, right? It could be like 0.001 or whatever, like some very small number. So what does that look like? Something that rejects low frequencies and passes high frequencies. So it's a high pass. So now you can make a low pass filter and a high pass filter. What do you think would happen if you put a high pass filter and then a low pass filter in series? You'd make a band pass filter. Or you can make a notch filter. Or you can make a whatever filter. You can start to get very creative depending what your needs are. Fun. Does anybody want to hazard a guess? Where's my cutoff frequency? That's right, I went there. I went there. What is my cutoff frequency? Can anybody suggest how I could calculate my cutoff frequency? Set what equal to root 2 over 2?
V equals 0.707.
Not V. Careful. The K. K is the amplitude of your output. Okay. So basically, we're going to say this question. Suppose V in equals cosine omega t. What value of omega makes V out equal root 2 over 2 cosine omega t plus some phase that we're not going to tangle with the phase right now. So all we're going to do, so this is what? This is your K. So I want to know what value of omega makes K equals to root 2 over 2. Well, we can do that, right? Because K, we want to get K equal to root 2 over 2. And K is simply equal to omega RC over root 1 plus omega RC squared equals root 2 over 2. Bet I could solve that for omega. Right? So all we'd have to do is solve that for omega. And I'd have my answer. Okay. How do I do that? What's my first step if I want to find the value of omega? Cross multiply or square. I'm going to have to do both of them, right? I need to cross multiply, and I need to square both sides. Let me go ahead and do that in one step. Actually, let's square it first. So if I square it, I get omega RC squared over 1 plus omega RC squared equals, right, the root 2 squared is 2. The 2 squared is 4, so 2 over 4 is a half. So square both sides. Then I cross multiply. So that's 2 omega RC squared equals 1 plus omega RC squared. And then, again, I'm solving for omega. Subtract that off. So that leaves me with omega RC squared equals 1, bless you. Square root of both sides. And you're left with omega equals. So your cutoff frequency is 1 over RC. And if I want to express my cutoff frequency in hertz, do I take this number and multiply or divide by 2 pi? Divide. Because omega is equal to 2 pi RC. So if I bring that over, sorry, omega is equal to 2 pi f. So if I divide by 2 pi, I'm just left with the f. And there you go. So, there you go. A nice end-to-end analysis. Let's do, I know we did this the other day for the low-pass filter. I think it was a good example, a good exercise. So let's go ahead and do this again real quickly. Let's let R equals 2K and C equals 3 microfarads. Let's do some math. 6 times 10 to the minus 3, that's a 6 of 1,000. A 6 of 1,000 is a third of 500 is, well, I don't know, 200. Okay, so let's suppose V in equals 7 cosine 300t. Find V out. Pretty straightforward. What do you think? Everybody figured out how to work complex numbers on your calculator? It's fine. Whatever. It's your test, not mine. Yes, sir.
Okay, so yeah, that see over there. That R is that just a reactance?
It's the resistance of our circuit. Remember I drew you this? It's that R.
Okay, like passive reactance is like 1 over 2 pi f, see?
Yeah, 1 over G omega C.
So,
I don't know, we just derived. That's the equation are you concerned about this equation? Are you concerned about this equation? It's just a unit conversion, right? If instead of expressing my cutoff frequency in radians per second, I want to express it in hertz, I just divide it by 2 pi.
I know, I'm just saying, like, I'm used to, like, when you're trying to find, like, the impedance of, like, a capacitor with frequency, and you use that same formula with the F.
Right, and that's how we started this whole conversation, right? We said that the impedance of the capacitor was 1 over G omega C.
Oh, then you just
It's sort of coincidental that it looks like that. I wouldn't let that trip you up. But yeah, I think it's just coincidental that they kind of look similar. Okay, so what's the deal? Like, how are we feeling about this? What's my output? What do I need to start with? Right. Let's start by finding K. So basically, I've got a formula for K, right? I've got values for omega. My omega is what?
300.
Right. For this particular problem, I'm setting omega equal to 300. So now all I'm really asking you to do is stick those numbers in your calculator. All right? And I'll try it too. Here's my calculator. Seriously, where's my calculator? Okay, so omega is 300, R is 2,000, C is 3 micro. Oh, this is going to work out great. Okay, so I'm going to square it. How do you square on this thing? Square it. So it's squared. 1 plus root reciprocal times. All right, I've got a value for K. Do you have a value for K? All right, 0.87. I can confirm. Anyone else? Thumbs up. Okay, good. Let's get the phase angle. So let's see, we're back to 300 times 2,000 times 3 micro. That was 1.8. Oh, so I'm just taking inverse tan of that. Sine pi 2 divide plus. Okay. In radians. 22 radians?
39. No.
I'm getting half a radian.
Yeah, I got 0.507.
Yeah. I agree with that. Half a radian is probably about 22 degrees. Right? If you take that, divide. Yeah, you just get your answer in degrees, I think. Okay. So, what's my final answer? What's my V out? We got K and theta, but I still don't have V out equals. So I'm getting a vote for 0.87 cosine 300t plus 0.5. That's almost the right answer. Ah, you have to multiply. Okay, so interpret, what does this 0.87 mean? It means that you take whatever your input was, this is like a multiplier that multiplies your input. So if your input was 1 cosine 300t, your output would be 0.87. But in fact, our input was 7 cosine 300t, so we multiply 7 times 0.87. 6.09. So it's good. Essentially what this is telling me is that, I mean, this is a rejection. We're starting to reject our signal, right? Our signal is only 87% the size that it was when it went in. Okay, so it's right on the cusp between getting passed and getting rejected. If I double my frequency, if we were to do this problem, and instead of this having be 300, I had it be 600, would you expect K to increase or decrease? It's a high-pass filter. So if I put in a higher frequency, I should expect it to get passed more, right? Which means that K would become closer to 1. Remember when we looked at this graph? Right, here's 1. We got what, 0.87? So we're operating right now right around here. That's 300. That's 0.87. So I'm saying if we double this to 600, what's my value of K? Bigger or smaller? Definitely, it's probably going to be a lot closer to 1. All right, and if I have my frequency, I'm going to expect something a lot closer to 0. Good? I'm going to leave this for you to put in Excel or MATLAB because I want to get on to the next one. Are you ready? This is where it gets ugly. I can no longer deny. I can no longer shield your eyes from what's about to happen. Remember this circuit? You didn't think we were done with it, did you? Oh yeah, I went there. Let me refresh your memory, because you've already forgotten. This circuit, depending on your choice for R, L, and C, well, a couple things happen. This circuit has a natural frequency that's equal to what? 1 over root LC. It also has a value of zeta that depends on R and C. Okay, but let's just say for right now it's proportional to, is it proportional? Yeah, it's proportional to the resistance. So the bigger the resistor is, the more the damping. Okay, the smaller the resistor is, the less the damping. This circuit can operate in one of two modes. It can either be underdamped, what are my values of zeta that give me underdamped performance? Less than 1 and greater than 0. You can't get negative zetas. So if zeta is between 0 and 1, you get underdamped performance. And the step response has what feature? Oscillations. It rings. Okay, remember the value of zeta determines how quickly the decay is. The closer zeta is to 0, the longer it takes to settle down. The other option is your system is overdamped, which happens when zeta is greater than 1. There's also the fancy pants special case when zeta equals 1, and I just refuse to teach that because really how often does that happen? Okay, what does my step response look like when the system is overdamped? Exactly. It looks a lot like the first order system. It basically, it settles without ringing. You remember all that, right? Okay. So, I mean, really, we did like 4 lectures, and that was really all you needed to get out of it. Okay. So, it won't surprise you to know that having completed the DC analysis, we're now going to do the AC analysis. We are going to put in an alternating current input, and we're going to talk about what comes out of the circuit. You with me? So, let us discuss. Okay, yeah, I just wanted to make sure I knew what I was getting myself into. So, we're just going to have time to get started, which is fine. Again, I'll be here on, I won't be here on Friday, but Elliot will be. And that doesn't mean class is optional, because the quiz that you'll be getting will definitely not be optional. What's that? What's hard? It's on exam 1. It will either be exactly one of the questions, or one of the questions with the numbers changed, or very similar to one of the questions, to the point that if you understood the question, you should understand the quiz. That would kind of be my... Well, it's actually, well, I already know what the quiz is going to be. I just don't want to tell you. But it'll fall somewhere in the words that I just said. Yes?
Is it not open note?
No. This time you're just going to do it. I'm only so reasonable, right? I mean, I told you the quiz is coming, and I told you it's on exam 1. I mean, if you want, I could also give you the solutions. But, man's got to draw the line somewhere. Okay. So, same business as before. V in is a cosine at some frequency. What's my V out going to be? Cosine at the same stinking frequency. Okay? All we got to figure out, magnitude and the phase. All right. Let's see if we can intuit our way through this before we actually start writing equations. So let's start by thinking about very, very low frequencies. So let's start with the inductor. What does an inductor, and remember the inductor equation is V equals L di dt. So at very low frequencies, what does an inductor do? What's that? Short circuit. So at low frequencies, your inductor looks a lot like a short circuit. Why? At low frequencies, what's di dt doing? If at low frequencies, would you expect di dt to be large or small? Small, right? If it's small change, if it's only changing very slowly, di dt will be small. Really small. 0 maybe. Okay? If di dt is 0 or very small, what's v going to be? Very small. Okay? So, does this look like a situation where the difference between the voltage across the inductor is 0? Yeah, so that's exactly what happens, right? If the frequency becomes so low, then the voltage across the inductor is 0. And, well, when the voltage across an element is 0, that's a short circuit, right, by definition. What about when frequency is large? What happens to your inductor? It's going to be the opposite, right? Whatever this one is, for large frequencies, it's going to be like an open circuit. Okay? At very large frequencies, there's going to be a giant voltage drop across the inductor to the point where it's basically just open. Okay? The capacitor does the opposite. Capacitor is I equals C dV dt. At low frequencies, what's your cap look like? At low frequencies, your cap looks like an open. Why? Because if dV dt is really small, which is exactly what happens in low frequency situations, remember low frequency means very small change. So if frequency is low, dV dt is small, and if dV dt is small, I is small. Well, what do you call it when there's no current flowing through an element? It's open. Is there any current flowing through this element? There is not. So that is consistent. What about at very high frequencies? It's the opposite. At very high frequencies, the cap shorts. Okay, so let's use that analysis to make some back-of-the-envelope calculations on this circuit. At very low frequencies, let's see, what's my circuit going to look like at very low frequencies? What's the inductor going to look like? Short. And then I've got my resistor, and then I've got my capacitor, which is an open. And this is V out. So what do you think in this case is going to be the relationship between V in and V out? They're going to be the same, right? Is there any current flowing in the circuit? No. So remember, this is omega small. This is the low frequency approximation. There's no current flowing in the circuit because there's an open here. If there's no current, what's the IR drop across that resistor? 0. If there's no IR drop, then this voltage has to equal that voltage. So in this case, V out equals V in. Good. Okay, let's try for large frequencies now. So for large frequencies, your inductor is an open. For large frequencies, your inductor is an open, and your capacitor is a short. What's my output voltage? 0. We've shorted our output to 0. What kind of circuit do we have? We got ourselves a low-pass filter, something where on low frequencies, V out equals V in, and on high frequencies, V out equals 0. What makes this circuit fun is two things. One is that it's going to be a little bit more selective of a filter than the first low-pass filter that we looked at. It's a two-pole filter, a second-order filter. So it's going to do a better job of rejecting frequencies above the cutoff. And secondly, what goes on here in the middle is going to be really interesting. Really interesting. Any guesses for, roughly speaking, where the cutoff frequency is going to be? Where L and C are equal? Maybe close to this number? I don't know if it's exactly omega naught, but it's in that ballpark. And that shouldn't surprise us because that's the sweet spot of the circuit. Okay, so when you come in on Friday, what you'll do with Elliott is you'll take the phasor notation for the inductor, the phasor notation for the capacitor, you'll do the voltage divider equation, you'll work a ton of math, and hopefully when you're done and you plot it, you will get a low-pass filter.